Have you ever paused to truly consider the invisible symphony that makes our digital world hum? I mean, think about it. One moment you're streaming a pristine 4K video, the next you're collaborating seamlessly on a document with colleagues continents away, or maybe refreshing a social media feed with updates from thousands of miles across the globe, as if by magic, appearing instantly at your fingertips.
It absolutely feels like magic. Yet behind that effortless experience lies an incredibly intricate and dynamic system. It's really a testament to human ingenuity, layer by layer over decades.
And that right there is the heart of our deep dive today. The profound yet foundational world of networks in the cloud. Our mission really is to cut through the complexity and give you a swift, impactful understanding of the essential technologies powering our digital lives. We're going to unpack the core concepts, unearth some truly surprising facts, and crucially, help you grasp what business professionals really need to know to navigate and leverage this omnipresent digital infrastructure.
Yeah, and we've synthesized a pretty comprehensive array of materials for this deep dive. We're aiming to offer not just a structured overview, but really the connections and implications that make these concepts truly meaningful. It's about moving beyond just definitions to strategic understanding.
Okay, let's unpack this then with a big question. What is the internet at its most fundamental level? Our sources describe it as the ultimate network of networks.
That's a perfect encapsulation, really. Imagine not just millions, but actually billions of computers, servers, and devices, all interconnected globally. It's not a singular monolithic thing, but rather an expansive sort of self-organizing web of countless individual networks.
Okay, and how do those connections happen physically?
Well, these connections are primarily forged in two main ways, either wirelessly through the air via technologies like Wi-Fi and various radio waves, or through physical cables, forming a vast, often unseen global grid under the oceans and underground.
And the daily impact of this network of networks is just monumental. It means instant access to an almost unfathomable ocean of data and resources on demand, practically anywhere on the planet.
Exactly.
For businesses, I mean, that means unprecedented market reach and operational agility, doesn't it?
Precisely. It's the engine driving, well, everything from your morning news scroll to the global supply chain systems that deliver goods to your doorstep to critical business applications that span international borders. Without this foundational network of networks, the digital economy and society as we know them would simply collapse.
So if this is a network of networks, how does all this information actually speak across these myriad connections? It's not like we're sending literal photos or documents as they appear on our screens, right? There has to be a more fundamental language.
You're absolutely right. The internet communicates in a much simpler, more fundamental language, binary information. We call these bits. Every single piece of information on the internet, every image, every word, every video, every financial transaction is ultimately broken down and transmitted as sequences of ones and zeros.
Ones and zeros. It sounds almost primitive for something so complex.
It is at its core. A bit is the smallest unit of digital information representing one of two states. A 1 meaning on or 0 meaning off. You can think of it like a tiny light switch that's either flipped on or off, or maybe a minuscule electrical pulse that's either present or absent.
Okay.
And these minuscule signals, whether electrical pulses or light pulses, are sent over the air via radio waves, like with Wi-Fi, or through various types of cables, like a fiber optic line.
Wow. So that binary simplicity is the foundational digital DNA for everything. This humble bit underpins even the most complex algorithms. Now, here's where it gets really interesting, I think. Trying to wrap your head around how much data these bits represent and the sheer scale they enable. Our sources give us a fantastic hierarchy of data units that makes this tangible.
Yeah, this is where the scale becomes truly mind-boggling. 8 of those individual bits are grouped together to form 1 byte. A byte is roughly equivalent to a single character like the letter A or the number 7.
Okay, 1 character per byte.
And from there, the units expand exponentially, usually in powers of 2, close to 1,000. So 3064 bytes make up a kilobyte.
Kilobyte. Okay.
Then 3054 kilobytes create a megabyte.
Megabyte, got it. Like a song file, maybe?
Exactly. And then we get to gigabytes, which are 224 megabytes. Your phone storage is probably measured in these.
Right.
And finally, for really large storage, 124 gigabytes form a terabyte. These are the fundamental data units that build our digital world.
So to really put that into perspective, our source materials mention an average smartphone, maybe with 512 gigabytes of storage, can hold something like 350,000 books. That's not just a lot of memory for photos. It highlights the incredible efficiency with which digital information is stored and transmitted. Imagine carrying around, well, almost 500,000 books in your pocket.
It truly does. And this incredible density isn't just about personal storage. It underpins the entire big data and AI revolution. Every complex analytical model, every massive data set that drives business intelligence, every machine learning algorithm, they're all built from trillions upon trillions of these minuscule bits.
Wow.
So it really reveals how foundational this sort of basic concept of binary information is to cutting-edge enterprise technologies and the vast opportunities they unlock for businesses.
Now, these bits don't just float magically from one device to another, do they? They need physical pathways, a network of highways to travel on.
Mhm.
Our next segment is all about these invisible and visible transmission mediums through which our data actually travels.
Indeed. We can broadly categorize these into wired, wireless, and even space-based transmission methods. Each has distinct characteristics and optimal uses. The choice of medium often has significant implications for speed, reliability, cost, and ultimately a business's operational efficiency.
Let's start with wired transmission, the physical connections. What are the main players here, and why do they matter for, say, a business?
Okay, well, the fastest and most advanced is fiber optic cable. This technology transmits data as pulses of light through extremely thin strands of glass fiber. It offers really unparalleled speed, often hundreds of gigabits per second, and immense capacity. It's basically the bedrock of modern internet infrastructure.
So high speed, high capacity.
Exactly. For businesses, fiber optic isn't just fast, it's incredibly reliable and resistant to electromagnetic interference, which is crucial for data centers and high bandwidth operations like video production or large-scale cloud computing.
So if your business absolutely depends on lightning fast, rock-solid connectivity, fiber is the gold standard.
Absolutely. Then we have copper cable, which transmits electric signals instead of light. This category includes twisted pair cables, which you'd find in older telephone lines and some early Ethernet networks.
Right, the phone jack kind of thing.
Exactly. And also coaxial cables, often used for cable TV and cable internet connections. While generally slower than fiber, especially over longer distances, copper is still incredibly common due to its existing widespread infrastructure and, frankly, lower installation costs for shorter runs. It's often the last mile connection into homes and smaller businesses.
And Ethernet. That's a term we hear all the time. Most of us have probably plugged an Ethernet cable into our laptop or router, or maybe seen them connecting servers in a data center rack.
Exactly. Ethernet isn't just one type of cable, but actually a set of standards for local area networking. And it can use either copper or fiber optic cables, depending on the speed and distance needed. Its primary role is connecting devices within a confined space, like an office building, a home network, or within those server racks you mentioned. It provides a stable, high-speed, and reliable connection, which is paramount for internal business operations where speed and consistency are key.
Okay, so that's the physical stuff, the cables we can conceptually grasp, even if they're hidden in walls or under streets. But what about wireless? That's where a huge portion of our daily digital interactions happen, untethered.
Right. Wireless transmission relies on various forms of electromagnetic waves traveling through the air. Radio waves are perhaps the most ubiquitous. They power our Wi-Fi networks, the cellular connections for our smartphones like 4G and 5G, and short-range things like Bluetooth devices.
Basically everything mobile.
Pretty much. These are what allow us to be mobile and connected without being physically tethered, enabling things like mobile workforces and smart offices. For longer distances or more specialized uses, we have microwave links. These are often used for point-to-point connections between buildings where laying cable is impractical, or for essential satellite uplinks connecting ground stations to satellites.
Okay.
And then there's infrared, which most people recognize from their TV remote controls. It's used for very short-range data transmission that requires a direct line of sight. It's niche in networking now, but still a familiar example of wireless data.
It's truly amazing to think about how all these different technologies coexist,
Yeah.
each optimized for a specific scenario. But then we also have space-based connectivity, which takes things literally to another level, providing internet access from orbit.
Yes, satellite and space-based connectivity are absolutely crucial for global reach, particularly in remote or underserved areas, and also for mobile platforms like ships and aircraft. We generally talk about three main types here, based on their orbit altitude. First, geostationary satellites, or GEO satellites. These orbit at a very high altitude, about 22,000 miles above the Earth's equator. This high orbit means they appear to stay in a fixed position relative to the Earth's surface, which allows them to provide broad, consistent coverage to vast regions with just a few satellites.
Right, so good coverage. What's the catch?
The trade-off is significantly high latency, or delay. Because the signal has to travel such an immense distance up to the satellite and back down, there's a noticeable lag.
So that's why sometimes satellite internet feels a little slower, even if the raw bandwidth is good, the shoot travel time.
Precisely. That round-trip time adds up. Then there are low Earth orbit satellites, or LEO satellites. These orbit much closer to Earth, typically just a few hundred miles up. This is where we see a lot of innovation now with constellations like Starlink and OneWeb.
Yes, Starlink.
Right. LEOs offer dramatically faster speeds and significantly lower latency compared to GEOs because the signal path is so much shorter. This makes them increasingly viable for mainstream broadband applications, even in densely populated areas, and they're certainly transforming connectivity in remote locations, opening up new business opportunities in previously unconnected regions.
So faster, lower delay. What's the downside there? Need more satellites.
Exactly. Because they're closer and moving faster relative to the ground, you need a large constellation of hundreds or thousands of them to provide continuous coverage. Finally, we have medium Earth orbit satellites, or MEO satellites, which sit in between GEO and LEO in terms of altitude. They're primarily used for navigation systems like GPS, GLONASS, Galileo.
Quote EPS.
Right. But they also find some applications in specialized broadband services, offering a kind of balance between coverage area and latency.
It's incredible to consider that when you're just clicking a link, your data could be traversing a fiber optic cable under the ocean, bouncing off a satellite thousands of miles above, or just zipping through the air via radio waves in your own home. For you, the listener, think about which of these have you used, maybe without even realizing it. And how critical do you think each one is for maintaining our global internet connectivity and supporting all the diverse business needs out there? It's pretty mind-boggling when you picture that global web of infrastructure.
Each medium plays a crucial, really complementary role. They fill specific needs and reach different corners of the globe, ensuring that our interconnected world remains just that, connected.
So we've talked about the how of data travel to the bits and the pathways. Now let's zoom out a bit and categorize these connections by their scope and proximity. Not all networks are created equal around. Our next segment delves into understanding specific network types: PAN, LAN, WAN, and the internet itself.
Right. So to start, let's define a computer network at its most fundamental level. It's simply a collection of two or more computers and devices that communicate with one another over transmission lines or wireless connections. That's it.
Simple enough.
From that basic premise, we then categorize them by their scope and proximity, basically, how close the devices are to each other. We usually move from the very personal, right around you, out to the global.
Okay, so the smallest and arguably most intimate type is the personal area network. Or what exactly does a PAN encompass, and why is it important for, say, a business professional to understand its implications?
A PAN connects devices immediately around a single person. Think wirelessly, and typically within a range of about 30 feet or 10 meters. It's like your personal bubble of digital connectivity.
A bubble.
For an individual, it's mostly about convenience connecting headphones, a watch, maybe a fitness tracker. But for a business, understanding PANs is actually crucial for managing device security and data flow, especially when employees use personal devices for work, the whole BYOD, bring your own device, trend.
Ah, right. So my Fitbit syncing with my phone, my wireless headphones connected to my laptop, a smartwatch communicating with my phone, maybe even an iPad printing wirelessly to a small personal printer right next to it. Those are all examples of devices within my PAN.
Precisely. They enable seamless, short-range communication between your personal devices for convenience, automation, and often enhanced productivity. And within PANs, we have specific wireless technologies. Bluetooth is the one most people are familiar with.
Definitely.
It has that typical range of up to 30 feet, maybe a bit more now. Common uses are music streaming to headphones or speakers, connecting peripherals like keyboards and mice, fitness tracking, basic file sharing between phones. It's ideal for that constant, low-power, short-range data exchange.
But there are other types too, like Zigbee. I've heard that name usually mentioned with smart homes, but I'm curious about its business applications. Is it just for light bulbs?
Not just light bulbs, though that's a common one. Zigbee is a low-power, low-data rate wireless technology designed specifically for, yes, smart home devices like lights, locks, and thermostats, but also, very importantly, for industrial sensors.
Ah, industrial. Okay.
Right. Its effective range can be much greater than Bluetooth, potentially up to 300 feet, and critically, it often uses a mesh network architecture.
Mesh network. What does that mean?
It means the devices can relay signals for each other, so a signal doesn't have to go directly from the hub to the device. It can hop from device to reach its destination. This creates a robust, self-healing network that can cover a larger area reliably.
Okay, that makes sense for sensors spread out in a factory or building.
Exactly. For businesses, Zigbee is critical in IoT deployments, Internet of Things, for things like environmental monitoring, asset tracking, smart building management, where you have maybe hundreds of low-power sensors that need to communicate reliably over a broader area without draining their batteries.
Got it. And NFC, near field communication. I use that all the time for payments without even thinking about it. Works.
Many people do, and it's a brilliant example of how technology fades into the background when it works well. NFC enables instant, contactless communication, but only within a very, very short range, typically about 2 inches or less.
2 inches, that's tiny.
It's designed that way for security. It's for quick, secure exchanges, mobile payments with Apple Pay or Google Pay, using contactless key cards for building access control, interacting with smart tags for inventory management, or even quick device pairing, tapping phones together. Its extreme short range actually enhances its security for transactions because you have to be right there.
So for you, the listener, think about where you've used these technologies recently. Bluetooth headphones, maybe a smart lock using Zigbee, tapping your phone to pay with NFC. And from a business perspective, why do we need all three, Bluetooth, Zigbee, and NFC, when they all connect devices nearby?
Well, it's because each one serves a slightly different, optimized purpose based on things like range, power consumption, the amount of data they need to send, data rate, and crucially, the security and immediacy requirements of the application.
Right, so different tools for different jobs, even within that personal bubble.
Exactly. What's fascinating here is how specialized they are. Bluetooth is great for that constant personal streaming and device interaction. Zigbee is perfect for creating a wide mesh of low-power IoT sensors across a building. And NFC is optimized for those ultra-fast, highly secure, close proximity interactions like a point-of-sale transaction or tapping an access card. Understanding these nuances helps businesses choose the right tech for the right job, ensuring efficiency and security.
Okay, moving up in scale from the personal bubble, we have the local area network, or LAN. This is probably what most people instantly think of when they hear the word network, like the office network or home Wi-Fi.
That's right. A LAN connects computers and devices that reside within a single geographically confined location. That could be your home, a single office floor, an entire building, or even a university campus. It can range in size from just 2 devices in a small home office to several hundred, maybe even thousands, in a large corporate building. All the devices on the LAN are typically connected to a central switch or router.
And the key emphasis here is the single geographic location, right? It doesn't stretch across cities.
Exactly. That's the defining characteristic. It's local.
So my home Wi-Fi network, connecting my laptop, phone, smart TV, and maybe a printer, is a classic example of a wireless LAN.
Absolutely. Within LANs, Wi-Fi, which technically stands for wireless fidelity, though we just call it Wi-Fi, is the most common technology for a wireless LAN, or double LAN. Its typical indoor range is 100, 300 feet, that varies significantly with walls, floors, and interference from other devices.
Definitely varies.
And speeds have vastly improved with newer versions like Wi-Fi 6 and now Wi-Fi 7, which offer faster data rates, lower latency, and better performance, especially in crowded environments with lots of devices trying to connect at once. Wi-Fi is the go-to for convenient internet access and internal network connectivity for almost all personal and business devices today.
So for businesses, having a robust Wi-Fi LAN is essential for employee mobility within the office, supporting guest access, and integrating a growing number of smart devices like printers, cameras, or even thermostats.
Absolutely critical. And then there's Li-Fi, which sounds incredibly futuristic. Light fidelity?
Li-Fi. Is that really a thing yet?
It is, though it's still quite niche. Li-Fi, or light fidelity, is an emerging technology that uses visible light communication, essentially flickering LED lights incredibly fast, instead of radio waves to transmit data.
Using light bulbs to send data.
Basically, yes. It can potentially be much faster than Wi-Fi, offering speeds in the gigabits per second. But it has a significant limitation. It requires a direct line of sight between the transmitter, the light fixture, and the receiver, a dongle on your device, and it obviously doesn't pass through walls or obstacles.
Ah, okay. Line of sight. That limits it.
It does. Its common uses currently include highly secure indoor communication in environments where radio frequency interference is a major concern, like hospitals or aircraft cabins, or where you don't want signals leaking outside a room, like secure government facilities. It's also used in smart lighting systems where the light fixtures can pull double duty as data transmitters. Think of it for secure, high-speed data within a specific room.
Interesting. So, thinking about your home Wi-Fi, that prime example of a wireless LAN in action. It's like an invisible bubble of connectivity emanating from your router, allowing all your devices to talk to each other and share that internet connection.
It is. It's all about that central router acting as a hub. It broadcasts radio signals carrying data to your devices, and it routes traffic between them and also out to the broader internet via your modem. For businesses, managing and securing their LANs, both the wired parts and the wireless parts, is a critical operational task. It impacts everything from internal collaboration and productivity to data security and preventing unauthorized access.
Okay, so beyond the local area, beyond the single building or campus, we hit the wide area network, or WAN. This is where things really start to stretch out geographically, sometimes even globally, right?
That's exactly right. A WAN connects computers and devices at 2 or more different geographic locations. The key here is different locations. These connections literally leave one site, travel over public or private telecommunications links, like fiber optic lines leased from a telecom company or even satellite links, and arrive at another site. Most large companies, especially those with multiple branch offices, remote workers, or global operations, operate one or more WANs.
So the WAN is the nervous system connecting their distributed enterprise.
That's a great way to put it. It ties all the disparate parts together.
So if a company has its headquarters in New York and a manufacturing plant in Shenzhen, or maybe a sales office in London, they're connected via a WAN.
Yeah.
And that connection is crucial for their global operations, for sharing data, coordinating activities.
Precisely. And just like PANs and LANs, WANs have powerful wireless options too, which are becoming increasingly important. Cellular networks are the most obvious example. This is what our mobile phones and tablets use to access the internet and communicate from almost anywhere.
Right. 4G, 5G.
Exactly. We've seen an incredible evolution there. 4G LTE, long-term evolution, brought us fast mobile internet, enabling things like video streaming and robust app usage on the go. 5G is the latest generation rolling out now. It offers even faster speeds, significantly lower delays, that latency we talked about, and the ability to connect a massive number of devices simultaneously in a small area.
And 5G isn't just about faster movie downloads, is it? It has bigger implications.
Definitely. It's ideal not just for enhanced mobile broadband, faster video calls, smoother gaming, but it's foundational for business applications like mobile point-of-sale systems, remote machinery control in factories, telemedicine, and supporting the rapidly expanding Internet of Things, IoT. It's how entire mobile workforces stay connected and productive from anywhere.
Okay. What about fixed wireless access? I've heard that's making big waves, particularly in rural areas where getting cables is hard.
Yes, fixed wireless access, or FWA, is becoming quite significant. It delivers home and business internet using radio signals, similar to cellular, but specifically for stationary locations, hence fixed. It bypasses the need for physical cables running to the building.
So like using a cellular signal, but for your home or office internet instead of your phone.
Essentially, yes. It often uses cellular towers or sometimes dedicated wireless infrastructure. It's an increasingly viable alternative to traditional wired broadband, like DSL or sometimes even cable, especially in rural or difficult-to-reach areas where laying fiber or even upgrading copper lines is prohibitively expensive. It can offer pretty decent speeds.
That could be a game changer for bridging the digital divide.
It certainly helps. And then, of course, there's satellite internet, which, as we discussed earlier with the different orbit types, uses satellites in space to provide internet access almost anywhere on Earth, even the most remote locations. While it can have higher latency, especially with GEO satellites, it's invaluable for areas with no other options, or for critical applications like internet on airplanes, ships at sea, or remote construction or mining sites.
So, for you, the listener, which of these WAN technologies have you used recently? We often take cellular connectivity like 5G for granted on our phones, but what about fixed wireless for your home internet? Or maybe satellite if you live remotely or travel? Think about how these technologies expand not just personal access, but the global reach and operational possibilities for businesses.
Yeah, each of these WAN technologies overcomes geographical limitations in different ways, creating a truly interconnected global economy. They are key drivers for business expansion, remote work enablement, and operational resilience in the face of disruptions.
And finally, after PAN, LAN, and WAN, we revisit the big one, the overarching connection that ties everything together, the Internet. How does that fit into this typology?
The internet is simply the ultimate network of networks. It connects countless individual LANs, WANs, and other specialized internets like academic or government networks globally. It's the grand aggregator, the global backbone built on standardized protocols that allows any connected device to potentially communicate with any other connected device anywhere in the world.
Okay. And you mentioned private internets.
Right. It's worth noting that sometimes a private version of the internet, used only within a single organization for internal communication and resources, is called an intranet. It functions much like the public internet, using the same technologies like web browsers and IP addresses, but is secured and isolated from public access, usually behind firewalls.
Now, it's important to clarify something here. LANs and WANs can exist with or without internet access,
Yeah.
right? They're not automatically synonymous with being online.
Absolutely. That's a crucial distinction. While most organizations today do integrate their LANs and WANs with the global internet for broader reach, access to cloud services, communication with partners, and so on, you absolutely can have an internal network that is entirely isolated,
Why would you do that?
usually for security or specific operational reasons. For example, a highly secure government agency might operate an internal LAN or WAN that is completely air-gapped, meaning physically disconnected from the public internet to protect highly classified information. Or a manufacturing plant might have a network controlling critical industrial machinery that's kept separate to prevent any possibility of external cyber attacks disrupting production. So it's a common misconception that network automatically means internet connected. You can have private, isolated network.
Okay, that makes sense. So now that we understand the different types of networks based on scope, personal, local, wide area, and how data travels through various mediums, how does the internet actually guide all that data home? How does it unerringly find the right device out of billions connected worldwide? This brings us to section 2, the internet's inner workings, starting with your device's unique address.
Exactly. And that unique address is the IP address, or Internet Protocol address. Think of it as the digital home address, or a unique postal code for every single device connected to a network. That network could be the global internet or just your local home network.
The unique number for every device.
Right. Its purpose is absolutely fundamental. It's a unique numerical label assigned to each device, allowing it to send and receive data packets. It ensures that information reaches the correct destination and isn't misdirected or lost in the vastness of the network.
So when I visit a website, my device announces its IP address with the request, saying, hey, send the web page back here. And the website server knows exactly where to send all that juicy data back.
That's precisely it. Without an IP address, data would have no specific destination. Global communication would be utterly impossible. It's the foundational addressing system.
Okay. And you mentioned different types, public and private.
Yes. We generally distinguish between public IP addresses and private IP addresses. This is important for network management and security. A public IP is the address assigned to your entire home or business network by your Internet Service Provider, ISP. It's how your network is seen and identified on the broader public internet. Think of it as the main address for your house or building.
Okay, the one the outside world sees.
Right. A private IP, on the other hand, is used only within your local home or business network, your LAN. Your router assigns these private addresses, often starting with 192.168 or 10, to individual devices like your laptop, phone, printer, etc. This allows them to communicate with each other locally, through the router, without each device being directly exposed to the public internet. It provides an initial basic layer of security through something called network address translation, or NAT, which your router handles.
So my laptop has a private IP inside my house, but when it goes out to the internet, it uses the public IP of my whole house network.
Yes, your router acts as the intermediary. Now, how are these addresses assigned? Is it random or fixed?
Good question. Does my phone always have the same IP address?
Usually not, especially for public IPs. They can be set up in a couple of ways. A dynamic IP is automatically assigned, usually by your router for private IPs or by your internet service provider for your public IP. And importantly, it can change periodically, maybe every time you reconnect, or after a certain lease time expires. This is very common for home users and most mobile devices.
Why dynamic? Why change it?
It offers simplicity for the user, and more importantly, it allows ISPs to efficiently reuse a limited pool of public IP addresses among their customers. They don't need a permanent address for every single customer device if they're not all online simultaneously.
Okay, what's the alternative?
The alternative is a static IP. This is a fixed address that does not change. You usually have to specifically request and often pay extra for a static IP from your ISP. These are typically reserved for servers like web servers or email servers, web hosts, or network devices where a constant, predictable address is absolutely essential. Think about needing remote access to a specific work server or ensuring a website is always reachable at the same address. That needs a static IP.
Got it. Static for servers, dynamic for most of us at home. And I know there are different versions of IP addresses too. I've heard of IPv4 and IPv6, and something about us running out of the old ones.
You're absolutely right. That's a huge issue that led to the development of IPv6. IPv4 is the older, much more familiar format. It looks something 192.168.1.1, blocks of numbers separated by dots. The critical challenge with IPv4 is that it uses a 32-bit system for addressing.
32 bits, how many addresses is that?
It allows for approximately 4.3 billion unique addresses. Now, that sounds like a lot.
It does.
But with the explosive growth of the internet and the sheer number of connected devices today, not just computers and phones, but smart refrigerators, watches, cars, industrial sensors, everything, we effectively ran out of unique IPv4 addresses years ago. Techniques like NAT helped stretch it, but the fundamental pool was exhausted.
So IPv6 is the solution.
Yes. IPv6 is the newer, a 128-bit format. It looks much more complex, with 8 groups of hexadecimal characters separated by colons, like 2001.0db8.85a3, .0000.882e, .0370, .7334. The key thing is that 128 bits allows for an almost unfathomable number of unique addresses, something like 340 trillion addresses.
Okay, that should last us a while.
It should essentially solve the address scarcity issue for the foreseeable future. IPv6 also includes some improvements like built-in security enhancements. IPsec is mandatory, though not always used, and more efficient routing, making it a more robust and secure protocol for modern internet traffic. The transition from IPv4 to IPv6 is ongoing and complex, but it's essential for the internet's continued growth.
What are some of the most common uses for IP addresses that we experience every day, maybe beyond just loading a web page? Where are they critical?
Well, web browsing is the most obvious. The IP address is needed to connect your device to the web server hosting the site. But beyond that, think about online gaming and streaming. They rely heavily on IP addresses for establishing direct or server-mediated connections, and low latency is crucial, so efficient routing based on IPs matters a lot.
Right. Lag is the enemy.
Exactly. For remote work and VPNs, virtual private networks, IP addresses are the absolute backbone. They allow secure and authenticated access to company networks and resources from anywhere in the world, routing traffic securely based on IP. And increasingly, smart homes, the Internet of Things, IoT, and industrial control systems all use IP addresses for their devices to communicate over the Internet, enabling automation, remote monitoring, and data collection on a massive scale. Every smart light bulb, every sensor needs an address.
Given all that connectivity and the fact that these addresses identify devices, security must be a paramount concern for IP addresses and the networks they serve. How do we protect ourselves?
It absolutely is. Several tools and practices are critical. VPNs, as I mentioned, are crucial, especially for businesses and anyone concerned about privacy on public Wi-Fi. They work by masking your real public IP address behind the VPN server's IP, and they encrypt your connection, creating a secure tunnel for your data. This enhances privacy and protects sensitive information transmitted over potentially insecure networks.
So VPNs hide your real IP and encrypt the traffic. What else?
Firewalls are another essential layer. Whether it's software on your computer or hardware built into your router or corporate network, firewalls act as intelligent gatekeepers for network traffic. They examine incoming and outgoing data packets based on predefined security rules, using IP addresses, port numbers, etc., and block potentially malicious traffic or unauthorized access attempts before they can even reach your devices or internal network. Robust security settings on routers and devices are also crucial.
So IP addresses are truly the silent foundation, the addressing system enabling global connection, communication, and commerce. But remembering all those numbers, especially IPv6 addresses, would be an impossible feat for us humans. We remember names, not long strings of numbers.
Exactly. And that's where the internet's unsung hero comes in. The DNS, or domain name system. This is the critical system that makes the internet navigable for ordinary people.
The internet's phone book, right? That's the classic analogy.
That's a perfect analogy. DNS is fundamentally the internet's phone book. Its job is to translate those human-friendly, memorable website names called domain names, like google.com or your company's domain, into the machine-readable numerical IP addresses, like that 142.250.190.46 we mentioned, that computers actually need to locate each other on the network. Without DNS, we'd all be typing long strings of numbers just to check our email or browse the web.
So how does that translation actually happen when I type in a website, say thedeepdive.com, into my browser? Walk me through that.
Sure. It's a remarkably quick and efficient process, typically happening in just milliseconds behind the scenes. 1. First, you type that website name, the domain name, into your browser's address bar and hit enter. 2. Your computer, or rather your operating system, first checks its own local DNS cache to see if you visited that site recently and already know the IP address. If so, great, it uses that. 3. If not found locally, your computer sends a DNS query request to a DNS server. This is usually a server automatically assigned by your internet service provider, ISP, and its address is configured in your computer or router settings. 4. That ISP's DNS server checks its own cache. If it doesn't have the IP address, it acts as a resolver. It goes out and queries other DNS servers higher up the hierarchy, starting with root servers, then top-level domain, TLD servers for .com, .org, .uk, etc., and finally the authoritative name servers for that specific domain, the ones that definitively know the correct IP address for thedeepdive.com. 5. Once the authoritative server provides the IP address, the ISP's DNS server sends that IP address back to your computer. 6. Only then, once your browser has the correct IP address, does it initiate a connection to the website server using that IP address.
Wow, that sounds like a lot of steps, but it happens almost instantly. Why is this system so absolutely essential? It seems like an extra step compared to just using the IP address directly, but obviously it's not.
It's indispensable for 2 primary reasons. Firstly, as we said, it makes the internet vastly easier and more intuitive for humans to use. We remember words and names far better than long strings of numbers. Imagine trying to memorize IP addresses for dozens or hundreds of websites.
Impossible.
Secondly, and this is critically important for businesses and website operators, DNS allows websites to change their underlying IP addresses without affecting users. Let's say a website needs to move to a new hosting provider or upgrade its servers. The physical server's IP address will likely change, but all the website owner needs to do is update the DNS record associated with their domain name to point to the new IP address.
So users keep typing the same familiar website name, and DNS just points them to the new location behind the scenes.
Exactly. It provides a crucial layer of abstraction and flexibility, ensuring seamless continuity of service even when the underlying infrastructure changes. Businesses can switch hosting, add servers, or reconfigure things without breaking access for their customers.
What's fascinating here is that beyond just convenience and this flexibility, DNS offers some tangible benefits that directly impact business operations and the user experience. What are some of those?
Absolutely. Well-configured DNS contributes to faster access to websites. DNS servers are highly optimized for quick lookups, and they extensively cache frequently accessed addresses, reducing the need to go through the full lookup process every time. For global businesses operating websites with visitors from around the world, DNS can also help balance traffic loads across multiple servers.
How's it do that?
If a popular website uses several servers spread geographically to handle demand, DNS can be configured using techniques like GeoDNS or load balancing to direct users to the server that is geographically closest to them, or perhaps the one that is currently least congested. This improves website performance, reduces latency for the user, and enhances the overall user experience.
Okay, faster and smarter routing. Anything else?
It also supports various security features. For example, some DNS services offer filtering capabilities. They can maintain blacklists of known malicious websites, phishing sites, malware distributors, and simply refuse to resolve their domain names, effectively preventing users from accessing those harmful sites. This adds a valuable layer of protection, often implemented at the ISP level or through specialized secure DNS providers.
But as always, with great power comes great responsibility, or maybe great risks. There are also significant concerns associated with DNS that businesses in particular need to be aware of, aren't there?
Yes, definitely. DNS, while essential, can also be a point of vulnerability. There are privacy risks. Some DNS servers, particularly the default ones provided by many ISPs, might log your browsing habits every website domain you look up. This data could potentially be used for targeted advertising sold to third parties, or if compromised, expose your online activities. Using trusted, privacy-focused DNS providers can mitigate this.
Okay, privacy is one. What about security threats? Can DNS itself be attacked?
Yes, there are significant security threats. One common attack is called DNS spoofing or DNS cache poisoning. In this attack, hackers manage to inject false DNS information into a DNS server's cache. So when you try to visit your legitimate bank's website, the poisoned DNS server might give your computer the IP address of a fake malicious website designed to steal your login credentials.
Yikes. So you type the right address, but DNS sends you to the wrong dangerous place.
Exactly. It hijacks the translation process. There are also denial of service attacks against DNS servers themselves. If attackers can overwhelm the DNS servers responsible for a company's domain, then legitimate users won't be able to resolve the domain name to an IP address, making the company's websites and online services effectively unreachable.
And that leads to the third concern, downtime issues.
Right. Downtime is a major business concern. If your organization's DNS servers fail due to technical issues, misconfiguration, or a cyber attack, then nobody on the internet can find the IP addresses for your websites, your email servers, or other critical online services. They simply become unreachable because the phone book is broken. This can lead to significant financial losses, disruption of operations, and serious reputational damage. Ensuring DNS resilience, often through redundant servers and specialized providers, is crucial for business continuity.
Okay, so let's try and put this all together. We've talked about bits, networks, IP addresses, DNS. Let's trace the amazing journey of a web request. It's really a millisecond marvel that happens every single time we click a link or type an address into our browser. It's this incredible ballet of technology that we rarely, if ever, perceive.
It truly is remarkable when you break it down. Let's walk through it step by step, imagining your request traveling potentially across the globe and back in the blink of an eye.
Okay. So first, I start by simply entering a website address, the URL, like www.example.com, into my browser and hitting enter. It all begins with that simple user action, that intention.
Right. Step 2. Your browser does a quick internal check. It looks in its own local DNS cache and maybe operating system's cache to see if it already has the website's IP address stored from a very recent previous visit. If it finds it there, it skips the whole DNS lookup, saving precious milliseconds, and jumps ahead.
Smart. Cache first. But if it's
Not cached, it moves to the crucial third step, the DNS lookup. That's our internet phone book in action. Your computer sends that DNS query, usually via your home or office router first, to your configured DNS resolver, typically your ISPs.
And that resolver might have to ask other servers.
If your local network or ISP's DNS server doesn't have the IP address cached, the request is recursively forwarded up the chain to other global DNS servers. The root servers point to the TLD servers, for.com, which then point to the authoritative name servers, for example.com. Eventually, the authoritative server responds with the correct IP address for www.example.com.
And once it's found, that authoritative DNS server sends the IP address, let's say it's 93.184.21cs.34, back down the chain to your ISP's resolver, which then sends it back to your computer. Now my browser knows exactly where to go.
But before it actually sends the request to that IP address, your browser takes your request, like get the homepage for www.example.com, and breaks it down into small, manageable chunks of information called packets. It's done for efficiency and resilience. Imagine trying to send a huge single file through a complex network. If any part gets corrupted or lost, the whole thing fails. By breaking it into small packets, if one packet gets lost or delayed, only that small piece needs to be resent. Also, smaller packets can navigate congested networks more easily.
Okay, like sending a book page by page instead of the whole volume at once.
Each data packet is like a small digital envelope. It includes the destination IP address, where it's going in the web server, your device's source IP address, where it came from so the server knows where to reply, a sequence number so the packets can be reassembled in the correct order when they arrive, and of course, a small piece of the actual data request itself.
These carefully addressed packets are then sent from my device, perhaps over my home Wi-Fi network, to my home or office router.
That's the next hop. They travel wirelessly using radio signals from your device's Wi-Fi antenna to your local router. From there, your router, acting like a local post office, forwards those packets onto your internet service provider's ISP's network. This connection from your router to the ISP might be via a cable modem line, a DSL phone line, or perhaps a super fast fiber optic connection if you have high-speed broadband.
Packets handed off to the ISP. And this is where the journey across the internet truly begins.
This is where they hit the wider internet highways. Your ISP's network analyzes the destination IP address on each packet and uses its own complex routing tables to determine the most efficient path for those packets to start traversing the internet towards the destination server.
And these packets might travel through many different networks and routers on their way.
These packets then embark on their journey through the vastness of the internet. They might move through multiple routers across major network backbones operated by large telecommunication companies, through internet exchange points where different ISPs connect, and potentially across continents via undersea fiber optic cables or satellite links. They might even take slightly different physical paths to reach their destination. Because they're individually numbered with sequence numbers and all contain the same destination IP address, the receiving server can reassemble them correctly upon arrival, regardless of the path they took or if they arrive slightly out of order. The routing decisions for these paths are dynamically determined by complex protocols running on the internet's core routers, the most important of which is BGP, the Border Gateway Protocol. Think of BGP as the internet's global traffic control system, specifically for routing between the major independent networks, called autonomous systems or AS, that make up the internet. Think large ISPs, big tech companies, universities. It's not concerned with routing within your home network, but how traffic gets from, say, Comcast's network to Google's network, or across international links.
So it manages the big highways, not the local streets.
Routers running BGP are constantly exchanging information with their neighbors about which networks they can reach and what the best path is, based on factors like fewest network hops, network policies, or avoiding congestion. This constant negotiation and updating of routes is what allows the internet to be so resilient. If one major link goes down, BGP helps routers quickly find an alternative path for traffic to flow. It's fundamental to keeping the global internet connected and dynamically adapting to changes or failures. For any globally operating business, the stability and efficiency of BGP routing is critical for consistent service uptime.
So, BGP is the crucial dynamic magic behind the packets, finding the best path across the internet's complex web. And finally, after traversing potentially thousands of miles and multiple networks, they reach their destination server.
The target web server, identified by that destination IP address, receives all those scattered packets arriving from your device. Its networking software meticulously reassembles them in the correct order, using the sequence numbers, reconstructing your original request. The web server software then processes your request, for example, fetch the home page, gathers all the necessary files for the web page, the HTML code, the CSS style sheets, the JavaScript code, images, videos, maybe data from a database, and then prepares its own response.
And it sends the response back in packets, too.
The web server breaks the web page content into its own set of packets, addresses them to your IP address, which it got from your initial request packets, and sends them back out onto the internet. These packets then make the return journey, potentially via a different route, back through the internet to your ISP, to your router, and finally to your device, where your browser reassembles them and renders the web page on your screen.
And all of this, from my initial click to the server processing the request and starting to send data back, happens within milliseconds.
Often, it truly is an amazing, incredibly complex, yet remarkably efficient journey that happens billions of times every second across the globe.
In this whole amazing journey, who are the crucial intermediaries, the powerful entities sitting in the middle, making sure my request actually finds its way onto those global highways and that the response finds its way back to my house? We're talking, of course, about the gatekeepers, Internet Service Providers, or ISPs.
Right. An ISP is fundamentally a company that provides the connection for you, whether you're an individual at home or a business, to the actual internet. Think of the big names like AT&T, Comcast, Verizon, Spectrum in the US, or similar companies globally. They are an absolutely fundamental link in this entire digital chain.
And what is their specific crucial role in this complex data flow we just described? They seem to be positioned right at the nexus of everything connecting us to the wider world.
They absolutely are. Let's trace the request again from their perspective. When you take a website URL, your request goes from your device to your home or office router. The ISP receives that request from your router via your modem connection, cable, DSL, fiber. 2, its next critical role is to route the request out to the broader internet. They transmit your data packets from your local connection point onto their vast network infrastructure and then onto the major internet backbones using protocols like BGP3. Their network helps connect to the website's server, directing your request packets towards the correct destination autonomous system and ultimately the hosting server's IP address. 4, and finally, on the return path, the ISP is responsible for delivering the data back to you. The website's response packets travel through the internet back to the ISP's network, and the ISP routes them down the final connection line back to your home or business network router.
So what does this all mean for businesses and individuals? They are the essential link, the gateway, and their performance, reliability, and policies directly impact our ability to use the internet effectively.
They absolutely are. ISPs are critically important because they are the ones who provide the actual internet access technology, deploying and maintaining the fiber optic cables, the DSL lines, the cable infrastructure, the fixed wireless towers, or the satellite ground stations needed to deliver bandwidth to end users. They maintain this colossal network infrastructure, all those expensive cables, routers, and switches that ensures smooth data flow.
And the choices they offer matter.
For businesses, the choice of ISP and the specific service plan, including the service level agreement or SLA if they have one, are critical decisions. These dictate crucial factors like guaranteed internet speeds, upload and download, data caps or limits, if any, network reliability and uptime promises, customer support responsiveness, and often the initial security measures provided for your connection, like basic firewalling or DNS filtering. Without a reliable, sufficiently fast ISP connection, a modern business simply cannot connect effectively to its customers, its partners, its cloud services, or its own distributed workforce. They are the gatekeepers to the digital world.
Now, let's delve a little deeper into the specific ways we get connected. Both the physical connections coming into our buildings and the mobile advancements that allow us to get online from anywhere. We'll look at broadband options and mobile generations, charting this ongoing evolution of speed and access.
Okay. When we talk about wired broadband connectivity options, we're primarily referring to the physical cables that provide high-speed internet access directly into homes and businesses. These are generally the most reliable, high-capacity connections, commonly relied upon for stability and consistent performance.
First up is one of the older technologies, but still around, DSL, or Digital Subscriber Line. Many listeners might remember the days of dial-up, and DSL was the first big step up from that, using the phone line.
Exactly. DSL uses the existing copper telephone lines that were already run into most homes and businesses. While it's generally slower than newer cable or fiber options, typical speeds might range from maybe 5 to 100 megabits per second, Mbps. Depending on the distance from the telephone exchange, its big advantage was using existing infrastructure. It's still widely available in many areas, particularly older infrastructures or more rural regions where laying new cable or fiber hasn't been economical.
So for smaller businesses or homes in certain areas, it might still be the primary option.
It could be. It can be a cost-effective entry point for basic internet needs, but it generally won't support heavy cloud usage, multiple high-definition video streams, or large data transfers very well compared to newer options. Performance also degrades significantly the farther you are from the phone company's central office.
Okay. Then there's cable internet, which many of us probably have, often bundled with TD service. How does that work?
Cable internet utilizes the existing coaxial cable lines originally installed for cable television service. It uses different frequencies on the same cable to carry internet data. It's significantly faster than most DSL connections, often providing downloads between maybe 25 millipees up to 500 millipees, or even close to a gigabit, 1,000 millipees, in some areas now with newer standards like DCIS AC 3.1.
So a big speed advantage over DSL generally.
Yes, and it's also widely available in most urban and suburban areas where cable TV infrastructure exists. It's a very common choice for both home and business internet, easily supporting multiple users, streaming, cloud applications, and video conferencing. The main potential downside compared to fiber is that the bandwidth on the local cable loop is often shared among neighbors, so speeds might slow down during peak usage times in some areas. But overall, for businesses, cable often offers a good balance of cost and performance for many typical office needs.
And then the gold standard for wired connections, the one everyone seems to want if they can get it, is fiber optic internet.
That would indeed be fiber optic internet, sometimes called FTTH, fiber to the home, or FTTB, fiber to the business. As we discussed earlier, this technology uses incredibly thin strands of glass fiber to send data as pulses of light, making it incredibly fast and efficient. It's generally considered the fastest and most reliable internet option available today.
What kind of speeds are we talking about?
Speeds typically start around 100 Mbps and commonly go up to 1,000 Mbps, 1 gigabit per second or GBPs, or even higher now, with multi-gigabit services becoming available in some places. Critically, fiber often offers symmetrical speeds, meaning your upload speed is just as fast as your download speed.
Ah, that's a big difference from DSL and cable usually, where uploads are much slower. Why is that important for businesses?
It's hugely important for businesses doing things like large data backups to the cloud, hosting their own servers or applications, using high-quality video conferencing extensively, or transferring large files frequently. For these kinds of demanding applications, fiber is the preferred choice. It ensures minimal latency, delay, and maximum throughput data rate, which are absolutely critical for productivity and competitive advantage in many industries today. The main drawback is simply availability. Deploying fiber infrastructure is expensive, so it's not available everywhere yet, although rollouts are expanding.
So for you, the listener, which of these wired technologies have you used for your home or business? DSL, cable, fiber. Who are your internet carriers? It's interesting to consider how your physical connection profoundly shapes your digital experience and your business's capabilities, from basic browsing to heavy-duty cloud operations.
Each option comes with its own set of advantages: speed, reliability, cost, availability, and limitations, directly influencing your daily digital interactions, and for a business, its ability to innovate, collaborate effectively, and compete in the modern economy.
Okay, now let's shift from the wires coming into the building to the airwaves that connect our mobile devices. The evolution of mobile network generations has seen an incredible, almost unbelievable increase in wireless speed and capability over the last few decades. It's a fascinating history of exponential growth.
It's easy to forget how far we've come in a relatively short time. We started with 1G in the 1980s. This was the era of those early brick-like mobile phones, purely analog voice communication. Think basic, often crackly phone calls. Data speeds were negligible, around 14.4 kilobits per second, kbps at best, barely enough for anything beyond voice.
Just making a call, that was it.
Pretty much. Then came 2G in the early 1990s. This was a major leap to digital voice transmission, which was clearer and more efficient. Critically, 2G also introduced low-speed data capabilities, allowing for the first time things like SMS text messaging and very basic WA pausing on phones. Speeds were still slow by today's standards, maybe up to 244 kilobps with enhancements like GPRS or EDGE, but it was the start of mobile data. Then 3G arrived in the early 2000s, and this is where mobile internet really started to become usable. 3G technologies like UMPS and HSPA offered significantly faster data speeds, potentially up to a few megabits per second, MBPs, perhaps around 4 Mbps typically. This enabled things like mobile web browsing that wasn't painfully slow, sending emails with attachments, basic video calling, and the first wave of downloadable mobile apps. This was the era when the first real smartphones with functional internet access emerged.
At the beginning of the smartphone era. Then came 4G.
Yes, 4G, particularly 4G LTE, long-term evolution, rolled out widely in the late 2000s and early 2010s. This brought high-speed mobile internet as we generally know it today. 4G LTE offered much higher speeds, typically tens of Mbs, potentially reaching up to 100 Ps or more under ideal conditions. It also had lower latency than 3G. This enabled smooth, high-definition video streaming, responsive online gaming, high-quality video conferencing, and the widespread adoption of complex cloud-based mobile applications for both consumers and businesses. 4G really made the smartphone the central hub of our digital lives.
And now we're deep into the rollout and adoption of 5G, which started becoming available in the late 2010s. And as we discussed, this isn't just about faster phones for consumers, is it? It has much broader technological and business implications.
Not at all. While 5G certainly offers enhanced mobile broadband, potentially reaching peak speeds of multiple gigabits per second, 10 Gbps theoretically, its real significance lies in three key areas defined by the standards. 1, eMBB, enhanced mobile broadband. Faster speeds, higher capacity for dense areas. 2, URLLC, ultra-reliable low-latency communications. Extremely low delays, potentially as low as 1 millisecond, and very high reliability, crucial for things like remote surgery, autonomous vehicle control, or real-time industrial automation. 3, MMTC, massive machine-type communications. The ability to connect a huge number of low-power devices simultaneously in a small area, like millions per square kilometer, essential for the Internet of Things, IoT, smart cities, connected sensors, logistics tracking.
So it's really three pillars enabling a whole new wave of applications beyond just faster streaming.
Exactly. 5G is foundational technology for enabling the next generation of digital transformation across industries, supporting real-time data processing closer to the edge and connecting literally billions more devices. And looking even further ahead, researchers are already working on 6G, which is projected for widespread deployment sometime in the 2030s.
The 6G, what are they even imagining for that?
Well, The goals are still being defined, but the visions include truly hyperspeed connections, potentially reaching terabits per second or TBPS, even lower latency, integrating AI natively into the network, supporting advanced applications like truly immersive augmented virtual reality, AR/VR, holographic communication, and enabling an even more pervasive and intelligent Internet of Things. The scale of ambition is enormous.
Let me just try and put the speed increase into perspective for our listeners again, because it's staggering. From 1G at around 14.4 kLBPs to 5G potentially hitting 10 GBPs, which is 10 million kbps, that's roughly a 700,000-fold increase in theoretical peak speed.
Roughly, yes. The orders of magnitude are immense.
And if 6G reaches 1 TBPS, 1 million Mbps or 1 billion kbps, that's projected to be something like 70 million times faster than 1G. It's truly exponential growth in our ability to transmit data wirelessly, completely reshaping what's possible for personal connectivity, business operations, and societal infrastructure over time.
It absolutely underscores the relentless pace of innovation in connectivity technology and the ever-increasing demands placed upon our networks by new applications, more data, and more connected devices. For businesses, this means a constant need to understand these advancements, adapt their strategies, and leverage these new capabilities to stay relevant and competitive.
So we've explored the physical pathways, wired and wireless, and the foundational networks PAN, LAN, WAN, Internet that connect us all. Now let's go beyond the device itself, beyond just the local network, and embrace the concept that has fundamentally reshaped computing in the last decade or so. The cloud. This phrase is absolutely everywhere, but what is the cloud in practical terms, especially for business professionals who need to understand its implications?
That's a great question because cloud can seem a bit abstract. At its simplest, you can think of the cloud as a large internet-based resource pool for compute power, storage space, databases, networking capabilities, software, analytics tools, and even artificial intelligence, all delivered to you as a service over the internet, usually on demand.
So it's not just storing files online like Dropbox. It's much more than that.
Much, much more. While online storage is one service offered by the cloud itself represents a fundamental shift in how we access, utilize, and pay for computing resources. Instead of buying and managing your own physical hardware and software, you're essentially renting access to shared resources managed by large providers in vast data centers located all around the world. For businesses, it's about transforming IT infrastructure from a capital expense, buying servers, to an operational one, paying a monthly subscription.
Okay, that shift from CapEx to OpEx sounds significant for businesses. What are the key characteristics and benefits that have made the cloud such a dominant force, such a game changer?
There are several compelling benefits. First, as you alluded to, it significantly reduces the need for powerful local computing. You don't necessarily need the most powerful, expensive personal computers or massive on-premises server rooms if most of your heavy lifting, processing, storage applications happens remotely in the cloud. Your local device can often be simpler, just needing a good internet connection and a browser.
Thinner clients.
Second, it offers incredible accessibility and data durability or security. Your data and applications are typically stored and backed up across multiple redundant locations within the cloud provider's infrastructure. This makes them accessible from almost any internet-connected device anywhere in the world. And crucially, it dramatically reduces the risk of data loss due to a local device failure, like a laptop dying, a fire, a natural disaster, or even many types of cyber attacks targeting your local premises.
That immediately makes me think of disaster recovery and business continuity for organizations.
Yeah.
Having data offsite and replicated seems huge.
It's a primary driver for many businesses adopting the cloud. Third, software and applications can often be used remotely without local installation. Think about SaaS, software as a service, applications like Salesforce or Google Workspace. You don't have to install these large, resource-intensive programs on every employee's local hard drive. They simply access them securely over the internet via a web browser. This simplifies deployment and updates immensely.
Right. No more installing CDs or complex packages on every machine.
Fourth, the cloud fundamentally simplifies file sharing and real-time collaboration. When documents and data live centrally in the cloud, everyone accesses the same online information. This ensures seamless collaboration, guarantees everyone is working on the most current version of a document, eliminating those "which version is final" headaches, and allows multiple people to potentially work on the same thing simultaneously.
Collaboration is a big one. What about the IT headaches that often plague businesses managing servers, updates, security?
That's another huge benefit: reduced maintenance and management overhead. The underlying cloud infrastructure, the physical servers, storage systems, networking gear, data center facilities is owned, managed, secured, and constantly updated by the specialized cloud provider companies like AWS, Azure, Google Cloud. This significantly reduces your personal or organizational need for hardware maintenance, software patching for the underlying systems, security configurations at the infrastructure level, and even the physical space, power, and cooling required for servers. You offload a lot of that operational burden.
And it sounds like it could be significantly more cost-effective, especially for businesses that don't need massive computing power all the time.
It often, critically, the cloud typically operates on a pay-for-what-you-use or subscription-based pricing model. You only pay for the computing resources, CPU time, storage space, data transfer that you actually consume, often billed by the hour or even by the second. This avoids the large, risky, upfront capital expenditures, CapEx, required to purchase servers and equipment that might sit idle much of the time. It converts that unpredictable CapEx into more predictable operational expenses, OpEx.
Pay-as-you-go utility.
Very much a utility model. And finally, perhaps one of the most powerful benefits is immense flexibility and scalability. Need more storage space. Need to spin up 100 virtual servers to handle a sudden website traffic spike for a marketing campaign? With the cloud, you can typically provision those resources almost instantly, often through a web portal or automated scripts, within minutes. And just as importantly, you can scale back down just as quickly when the demand subsides, so you're not paying for resources you no longer need. This agility is transformative for businesses facing fluctuating demand or wanting to experiment quickly.
What's truly fascinating here, when you put it all together, is that the cloud allows individuals and organizations, even small startups, to tap into vast, almost limitless computing resources, the kind previously only available to huge corporations or governments, without actually owning or managing any of the underlying physical infrastructure themselves.
It's having access to a global supercomputer network, sophisticated databases, advanced analytics tools, and cutting-edge AI services, all on demand without having to buy, install, or maintain a single component of it. It truly democratizes access to powerful computing capabilities, leveling the playing field and fostering innovation.
And you mentioned the key services provided go way beyond storage.
The core services provided typically fall into broad categories: compute, virtual servers, serverless functions; storage, object storage, file storage; block storage for databases, relational, NoSQL, data warehousing; networking, virtual networks, load balancers, DNS; the actual software applications, SaaS, analytics tools, big data processing, business intelligence; and increasingly sophisticated artificial intelligence, AI, and machine learning, ML, services that businesses can leverage without needing deep AI expertise in-house.
This shift isn't just a convenience for individuals saving photos online. Organizations, as you said, are moving to the cloud in droves. This brings us to why organizations are making this massive transition. It seems like it's become less of an option and more of a strategic imperative.
That's a very accurate assessment. To really understand the magnitude of this shift, it helps to look at the historical context briefly. Before, say, roughly 2010, the vast majority of organizations, especially medium to large ones, operated primarily with an on-premises IT model.
On-premises meaning they owned and ran everything themselves.
Exactly. They built, maintained, and physically housed their own computing infrastructure in their own data centers or server rooms. This meant purchasing or leasing expensive servers, storage arrays, networking equipment, installing them, managing complex operating systems and databases, ensuring power and cooling, handling physical security, and employing large teams of specialized IT staff to support everything from internal email systems and company websites to critical e-commerce platforms and custom-built in-house applications.
That sounds incredibly expensive, complex, slow to change, and frankly very resource-intensive. It also feels like a huge potential distraction from what the company actually does, its core business mission.
It absolutely was, and often still is for companies with legacy systems. These on-prem solutions required significant upfront capital expenditure, constant ongoing maintenance and upgrade cycles. Remember, Moore's Law, hardware gets outdated fast. Huge energy consumption for power and cooling, specialized technical expertise that can be hard to find and retain, and a lack of agility. Provisioning a new server could take weeks or months.
Okay, so what changed around 2010?
Well, several things converged. Advancements in virtualization technology, allowing multiple virtual servers to run efficiently on single physical machines, significant increases in internet bandwidth availability and reliability, and the emergence of large specialized providers like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform GCP, who built massive, highly efficient data centers, and started offering computing resources as a utility service. This led to a rapid, almost wholesale shift, particularly after 2010, towards leasing computing infrastructure and services from these cloud providers instead of building and managing it all in-house.
And this trend is just accelerating.
Absolutely. The overwhelming likelihood, based on current trends and the compelling economics, is that in the not-too-distant future, nearly all computing infrastructure for most businesses, perhaps excluding some highly specialized or regulated cases, will be cloud-based in some form or another.
Here's where it gets really interesting, I think, from a strategic business perspective. This move to the cloud, in essence, is a powerful form of outsourcing. It allows organizations to offload the immense burden, cost, and complexity of managing physical IT infrastructure and all the associated headaches.
Precisely. Framing it as strategic outsourcing is key. This isn't just about potentially saving some money on hardware, though that's often a factor. It's a profound strategic pivot. By offloading the capital expense, the operational complexity, and the day-to-day management of IT infrastructure to specialized cloud providers who benefit from massive economies of scale and deep expertise.
Businesses can free up their own resources.
Exactly. They can reallocate precious capital, their valuable internal talent, shifting IT staff from managing servers to building value-added applications, and most importantly, their strategic focus towards what actually differentiates them in the marketplace, core innovation, developing better products and services, enhancing customer experience, or accelerating market expansion. It dramatically increases their business agility and market responsiveness.
So it's less about running servers and more about achieving business goals faster.
That's the core value proposition. It reduces the time to market for new ideas and services because you can provision the needed infrastructure in minutes, not months. It allows for rapid experimentation with low risk. If an idea doesn't work, you just shut down the cloud resources without having wasted huge capital investments. And it significantly enhances their competitive edge by allowing them to leverage cutting-edge technologies like AML services that would be prohibitively expensive or complex to build themselves. It's about leveraging the specialized expertise and scale of cloud providers so you can focus intensely on what makes your business unique and successful.
But the cloud isn't just one monolithic thing, is it? We hear terms like public cloud, private cloud, hybrid cloud. It seems there are different ways to actually set up and use cloud resources depending on an organization's specific needs, particularly around security, control, and cost. Let's explore these different cloud deployment models: public, private, hybrid, and maybe community cloud.
Yes, understanding these distinct deployment models is absolutely crucial for any business professional involved in technology decisions. The choice profoundly impacts control over data, infrastructure costs, security posture, regulatory compliance, and overall scalability. The first, and perhaps most common model people think of, is the public cloud.
Public cloud, like AWS, Azure, Google Cloud.
Exactly. These are cloud computing services offered by third-party providers over the public internet. The key characteristic is that the underlying infrastructure, servers, storage, networks, is owned and operated by the cloud provider and is shared by multiple organizations or tenants. Your data and applications run alongside those of other customers, although they are logically isolated and secured from each other.
Okay, shared infrastructure. What are the main pros and cons for a business using a public cloud?
The main advantages are typically cost-effectiveness and scalability. Because the resources are shared across many customers, the providers achieve massive economies of scale, allowing them to offer services at a lower cost than most organizations could achieve on their own. It's also highly scalable and elastic. You can instantly provision vast amounts of resources when needed and release them when you don't, paying only for what you use. The main perceived trade-off, or con, is often less direct control over the underlying infrastructure and potentially concerns about data security or residency, although providers invest enormous amounts in security and offer many compliance certifications.
So a classic use case example here, as mentioned in the source material, would be Netflix running almost entirely on AWS.
Exactly. Netflix needs to stream billions of hours of video content to millions of subscribers worldwide, with huge peaks in demand. They achieve this massive scale and global reach without needing to invest in and maintain their own physical server farms everywhere. They lease all that immense computing power, storage, and networking capacity from AWS's public cloud, allowing them to focus on their core business: content creation, recommendation algorithms, and user experience, not data center management.
Okay, public cloud clear. What about the opposite end of the spectrum, private cloud?
A private cloud is computing infrastructure that is used exclusively by a single organization. It's not shared with other tenants. This private cloud can be physically located on the organization's own premises, managed by their own IT staff, an on-premises private cloud, or alternatively, it can be hosted by a third-party provider, but on hardware that is completely dedicated to that one organization, a hosted private cloud. The key is exclusivity.
This sounds like it addresses the control and security concerns of the public cloud, but presumably at a higher cost.
Generally, yes. The primary pros are significantly enhanced security and greater control over your data, the infrastructure, compliance configurations, and operational policies. Businesses with very stringent regulatory requirements, like certain financial institutions or healthcare providers, extremely sensitive intellectual property, or specific security needs often opt for private clouds to maintain maximum control. The main downside is that it's typically more expensive than public cloud, as you're not sharing those infrastructure costs, and you bear more of the operational burden, either directly or through higher hosting fees.
Can you give an example of a private cloud user?
A good example might be a large government agency dealing with classified information, like the U.S. Department of Defense mentioned in the sources. They might use a private cloud, potentially air-gapped, to securely manage highly sensitive military data and mission-critical operations, where absolute control, data sovereignty, and stringent compliance are non-negotiable.
Okay, so public gives scale and cost savings, private gives control and security. What about the hybrid cloud? It sounds like it tries to get the best of both worlds.
It absolutely does, and it's becoming an increasingly popular model for many organizations. A hybrid cloud architecture combines elements of both public and private clouds, creating a unified, interconnected infrastructure where data and applications can be managed and moved seamlessly between the two environments as needed.
How does that work in practice? What's the benefit?
The core benefit is achieving a dynamic balance between flexibility and control. Businesses can leverage the scalability and cost-effectiveness of the public cloud for less sensitive workloads, development and testing environments, or applications that experience highly variable demand, bursting. Meanwhile, they can keep their most sensitive customer data, mission-critical legacy applications, or workloads subject to strict regulations within the enhanced security and control environment of their private cloud. Workloads can communicate across the boundary.
Can you give an example of a company using a hybrid approach?
A good retail example mentioned is Target. They might use a public cloud provider like Microsoft Azure for their public-facing website, allowing it to easily scale up to handle huge traffic spikes during holiday sales seasons. However, they might keep their sensitive customer transaction data, payment processing systems, or loyalty program databases on a private cloud infrastructure, perhaps on-premises or hosted, for enhanced security and compliance with financial regulations like PCI DSS. The two environments work together.
That makes sense, leveraging the strengths of both. And finally, there's the community cloud model. This one sounds a bit different, more collaborative.
It is. A community cloud is a specific type of cloud infrastructure that is provisioned for exclusive use by a specific community of organizations that share common goals, concerns, or requirements. Think of multiple organizations within the same industry vertical, or perhaps different government agencies or universities collaborating on research.
So multiple organizations share the infrastructure, but it's not open to the general public.
Exactly. The infrastructure might be jointly owned and operated by the community members or hosted by a third party specifically for that community. The main benefits include cost sharing among the participating organizations. It's cheaper than each building their own private cloud, and the ability to more easily meet specific compliance standards or shared operational needs relevant to that community. For instance, several healthcare providers in a region might use a community cloud specifically designed to meet strict IAP regulations for storing and securely sharing electronic patient records or large medical imaging files, benefiting from shared security frameworks and operational costs tailored to their specific needs.
Interesting. So 4 main models: public shared, scalable, cost-effective; private, exclusive, high control, secure; hybrid, mix of public-private for flexibility; and community, shared among specific group for common needs. Understanding these helps businesses choose the right foundation.
Absolutely. The choice of deployment model is a foundational strategic decision.
Now, these deployment models dictate where your data and applications physically or logically reside. But then within the cloud, there are also different types of cloud services offered, usually categorized as IaaS, POSes, and SaaS. These seem to determine how much of the underlying computing stack an organization manages versus how much the cloud provider handles for them.
Yes, if we connect this to the bigger picture of outsourcing IT, these fundamental cloud service types, infrastructure as a service, IaaS, platform as a service, POSIS, and software as a service, SaaS, represent different levels of abstraction and responsibility sharing between the customer and the cloud provider. Think of it as a spectrum, determining who manages what, from the raw building blocks up to the finished application.
Like rent to different levels of furnished apartments.
That's a pretty good analogy, actually. The choice among these often dictates a business's operational model, the kind of IT skills they need in-house, their level of control, and even their potential for competitive differentiation based on customizing the technology.
Okay, let's start at the bottom layer, the most basic offering.
Yeah.
IaaS, or infrastructure as a service. What exactly does it provide, and what does the business still need to manage?
I essentially provides the foundational virtualized hardware layer delivered over the internet. You're essentially renting access to fundamental building blocks like virtual machines, VMs, which are like virtual servers you can configure and run, scalable storage solutions like virtual hard drives or object storage, and basic networking components like virtual networks, firewalls, load balancers. This is the lowest level of service provided by the cloud vendor. Using your analogy, it's like renting an empty, unfurnished apartment building shell.
So the cloud provider handles the physical data center, the servers, the storage hardware, the core network, power, cooling,
Yeah.
physical stuff.
Exactly. The cloud provider owns and maintains the physical hardware, ensures it has power, handles basic physical security, manages the virtualization layer, the hypervisor that creates the VMs, and often handles backups and disaster recovery at the infrastructure level. They ensure the building itself is sound and the basic utilities are working.
So the user, the business, renting the IA, still manages a lot inside that virtual hardware. What's their responsibility?
Yes, the business using IS manages pretty much everything above that raw infrastructure layer. This includes installing, configuring, patching, and managing the operating systems like Windows Server or various Linux distributions on the virtual machines, installing and managing any middleware needed like database servers, web servers, application runtimes, and deploying, managing, and securing their own applications and data.
Okay, so still a significant amount of IT management just without owning the physical boxes. Who uses IS typically?
The use case is often larger companies, or those with specific technical requirements that want to get out of the expensive and burdensome business of owning and managing their own physical data centers and hardware. They want the flexibility and scalability of the cloud for infrastructure, but they still want or need full control over their operating system environments, their specific software stack, and how everything is configured. They might have highly customized legacy applications, specific compliance requirements that dictate OS-level controls, or in-house expertise they want to leverage for managing the software environment. It offers the most control among the cloud models, but also requires the most IT expertise from the customer. It connects back to Moore's Law, too. The provider keeps the underlying hardware current, which is a big benefit.
Got it. Maximum flexibility, minimum hardware hassle, but still manage OS and apps. Moving up a layer in the stack, we have PaaS, or Platform as a Service. This sounds like it provides more of the stack ready-made, simplifying things further.
It does. With PaaS, the cloud provider delivers not just the underlying hardware infrastructure, like IS, but also the operating systems, the middleware, like databases, messaging queues, development tools, and the runtime environments needed to build, test, deploy, and run applications.
So using the apartment analogy, this is like renting an apartment that comes with the walls painted, the plumbing and electricity working, and maybe even basic kitchen appliances like a stove and fridge installed.
That's a very good way to think about it.
Mm-hmm.
The platform is provided, ready for the developer to build upon. The cloud provider manages the infrastructure, the operating system patching and updates, the database administration, often, and the underlying network. The company using PaaS primarily focuses on developing, deploying, and managing its own applications and its own data. These applications and data are often the core, mission-critical assets that provide the company's unique value and competitive advantage.
So this seems ideal for companies, especially software development teams, who want to rapidly build and deploy applications without worrying about managing the underlying OS, servers, or databases. They just want to code and run their app.
Exactly. Paya significantly streamlines the entire software development, lifecycle coding, building, testing, deploying, scaling, and updating applications becomes much faster and more efficient because the platform handles much of the underlying complexity. Developers get pre-configured environments, development tools, APIs, and services that accelerate their work.
Can you give an example scenario for PayS?
Sure. Let's take the example from the source material involving a company using a large enterprise application like SAP. If they run SAP on a pay-as offering, say from Microsoft Azure or AWS, the company, let's call them Dana, as in the example, would own and manage their specific SAP application configuration and all their critical business data within SAP. However, the cloud provider, Microsoft, would own and manage everything else underneath: the hardware servers, the underlying operating system like Linux or Windows Server, the database software needed by SAP, the networking infrastructure, backups, security patching for the OS and database, etc. This allows Dana's IT team to focus entirely on optimizing their business processes within the SAP application itself, rather than spending time worrying about server maintenance, OS updates, or database backups.
Okay, so PayAs abstracts away the OS and middleware headaches, letting companies focus on their apps and data. Now, the highest level of service, the most abstracted, where the cloud provider manages absolutely everything, is SaaS, or software as a service. This is probably what most end users interact with daily, often without even thinking cloud.
That's absolutely right. With SaaS, the cloud provider manages the entire stack: the hardware infrastructure, the operating systems, the middleware, and the software application itself. The user, whether an individual or a business employee, simply accesses the fully functional software application over the internet, typically via a web browser or sometimes a thin client app.
So no local installation needed at all, no IT management required from the user side.
Correct. There's no need to install the software on your local computer, no need to worry about updates or patches. The provider handles all that centrally, and minimal IT maintenance required from the customer's perspective. It's like subscribing to a fully furnished, fully serviced apartment. You just move in, use the amenities, and pay your monthly rent. The provider takes care of everything else behind the scenes.
Like Google Docs, as you mentioned earlier, or Gmail, or Salesforce CRM, or maybe collaboration tools like Slack or Microsoft Teams.
Precisely. Those are all classic examples of SaaS. Google runs all the underlying infrastructure: the servers, the OS, the databases, the networking, and the Google Docs application software itself. Users just log in and use it. Other common examples include many email services, customer relationship management, CRM tools, enterprise resource planning, ERP systems, especially for smaller businesses, human resources software, project management tools, and countless other business applications.
One of the main benefits for businesses choosing SaaS.
SaaS solutions are ideal for businesses looking for immediate usability. Just sign up and start using. Minimal IT overhead, significantly reducing the need for internal IT support for that application.
Yeah.
Predictable subscription costs, usually per user per month, and automatic updates handled by the provider. The trade-off is generally the least amount of customization possible compared to PaaS or IA, as everyone is using the same centrally managed software version.
And the source materials mention a couple of other as-a-service options briefly, like DaaS and MaaS.
Yes, the as-a-service model is very flexible. DAS, Desktop as a Service, is where a provider hosts a virtual desktop environment in the cloud, and users access their entire desktop, OS, apps, data remotely from any device. It centralizes management and security for user desktops. And MaaS could refer to several things, but sometimes it's used informally and perhaps worryingly for malware as a service, where cybercriminals rent out malware tools, definitely not a legitimate cloud service. But the point is, the as a service concept can be applied to many different IT functions.
Okay, so choosing between IS, renting hardware, PaaS, renting hardware plus platform OS, and SaaS, renting the whole application, isn't just a technical decision, is it? It sounds like a fundamental strategic choice for a company.
It absolutely is. It shapes your company's agility, its IT cost structure, the type of IT talent you need to employ, your level of control versus convenience, and even your speed to market for new digital initiatives. There's no single right answer. The best model depends entirely on the specific application, the business needs, the company's resources, and its strategic goals.
So we've seen how networks connect us globally, and how the cloud provides these incredibly powerful and flexible computing resources, empowering businesses to offload vast amounts of IT burden and focus on innovation. But the cloud isn't static. It's constantly evolving, constantly pushing boundaries. What's next for this digital frontier, particularly as we generate more data than ever and push the limits of real-time interaction?
That's a great segue into the future because the cloud is evolving. This brings us to what many see as the next major shift: the evolving cloud and the rise of edge computing. One of the driving forces behind this next cloud evolution is addressing a current and increasingly critical bottleneck: data speeds, and more specifically, latency.
Latency, that delay we talked about. Why is that becoming such a bottleneck now?
Well, think about the sheer volume of data being generated today. especially from billions of Internet of Things, IoT devices, sensors in factories, connected cars, smart city infrastructure, wearable health monitors, security cameras. Add to that the demands of real-time AI applications, augmented reality, autonomous systems. Sending all of that massive amount of data back to distant, centralized cloud data centers for processing introduces significant latency. The round-trip time can simply be too long for applications that require instantaneous responses. It also strains the network bandwidth connecting the edge to the core cloud.
So the traditional model of sending everything back to a big central brain is becoming inefficient or too slow for some critical applications.
Exactly. For many emerging use cases, that delay is unacceptable. Think about an autonomous car needing to react instantly to avoid an obstacle, or a remote robotic surgery requiring immediate haptic feedback, or a smart factory needing real-time quality control adjustments. Milliseconds matter.
So the intuitive solution seems to be, don't send the data so far. Bring the processing closer to where the data is actually being generated, kind of like having mini data centers or local processing power nearby, but still connected to the larger cloud ecosystem.
That's precisely the core idea behind edge computing. It's about decentralizing computing resources. Instead of concentrating everything in a few massive centralized data centers, edge computing involves placing computing power, storage, and networking capabilities physically closer to where they are actually needed, out at the edge of the network, near the data sources themselves.
So maybe processing data right on the factory floor, or in a cell tower near connected cars, or even on the device itself sometimes.
Exactly. This involves deploying smaller servers, gateways, or specialized hardware at edge locations. The concept is often described as local storage, remote execution, or perhaps more accurately, localized execution. Data can be processed, analyzed, and acted upon locally at the edge, with only the necessary results, summaries, or critical alerts being sent back to the central cloud for longer-term storage, large-scale analytics, or model training.
This sounds like it could drastically reduce that critical latency issue and also improve speed and reliability for these time-sensitive applications, making things like autonomous vehicles, real-time medical monitoring, or instant factory automation much more feasible and robust.
Absolutely. By processing data locally at the edge, you minimize the distance it needs to travel, slashing latency often down to single-digit milliseconds. This enables the real-time decision-making required by many next-generation applications. It also reduces the load on the core network infrastructure, as less raw data needs to be transmitted back to the central cloud, potentially lowering bandwidth costs and improving overall network efficiency. Furthermore, it can improve reliability if the connection to the central cloud is temporarily lost. Edge systems can often continue to operate autonomously using local processing.
This really does feel like a significant evolution, maybe even a partial reversal of the trend towards massive centralization. It raises an important question, doesn't it? How will this increasingly distributed approach to computing, this blend of powerful central cloud capabilities with intelligent edge processing, further revolutionize how we interact with technology and data, especially with the exponential rise of IoT devices and the ever-increasing demand for instantaneous real-time responsiveness across every aspect of our lives and businesses?
It's poised to reshape many industries and experiences.
What an incredible journey we've taken today. Seriously, from exploring the smallest bits of information, those ones and zeros, traveling through this diverse ecosystem of networks, whether tiny personal area networks around us, local area networks in our homes and offices, or vast wide area networks spanning the globe, all guided unerringly by unique IP addresses, those digital street numbers, and translated by the Internet's essential phone book, the DNS.
Yeah, making it all usable.
All the way up to the truly transformative power of the cloud. We looked at its various strategic deployment models: public for scale, private for control, hybrid for flexibility, and community for shared needs, and the different service layers like infrastructure, platform, and software as a service, offering varying levels of outsourcing and control.
It's quite a stack of technologies, isn't it? We've really seen how these foundational pieces weave together, layer upon layer, to create the seamless, always-on digital experience that, frankly, we often take completely for granted nowadays.
We really do.
And hopefully, understanding these underlying concepts, how networks function, how data travels, what the cloud really means, isn't just for the IT professionals listening. We believe it's absolutely essential knowledge for anyone navigating and utilizing our increasingly connected world. It allows you, the listener, to grasp the why behind the what of our digital lives, make more informed decisions, whether personally or professionally, and understand the context behind so many business and technology trends today. It makes you well-informed in a world saturated with information overload.
Absolutely. And as we look towards the future, especially with this accelerating rise of edge computing that you just described, where processing power moves closer and closer to us, out from the distant data centers towards the devices and sensors all around us, it really makes you wonder, doesn't it? Considering how quickly networks in the cloud are evolving, what aspects of your own digital life or maybe your business operations do you think will be fundamentally reshaped by these technologies in the next, say, 5 to 10 years? Will your phone truly become just a window, a portal, to this powerful distributed intelligence that lives everywhere and nowhere simultaneously? Or will new, completely unforeseen needs and possibilities emerge from this edge cloud synergy that we can't even properly conceptualize today?
It's a fascinating question to ponder. The future of connectivity and computing promises to be every bit as dynamic, transformative, and full of surprising possibilities as its remarkable past has been.